All right, so we've got a block of ice placed on an inclined plane at 60 degrees. Ooh, that's steep. Okay. 60 degrees is the angle, not the temperature. Determine the acceleration if the coefficient of friction is 0.2. Okay, block of ice placed, determine the acceleration. Okay, so that tells us if it accelerates, we're realizing that this thing is moving. So mu sub k, the coefficient of kinetic friction, is 0.2. I'm going to draw some forces on here. Force of gravity points straight down towards the center of the Earth. The x direction is what I'm going to call down the plane. Y direction would be straight up. So there is a normal force that points up, and it tells us there's a force of friction that points backwards, which is equal to the coefficient of kinetic friction times the normal force. So I am going to do this part quickly. If you would like to see me go through the components, look at the video for number 4 and number 3. I think I go through it on both of those. But the force of gravity is going to be split into x and y components. We don't want to know the acceleration, the component of the acceleration down into the Earth, which would be not. We want to know the acceleration down this incline. Okay, so force of gravity in the y, that's going to be equal to the force of gravity. Okay, so this whole big number, whatever it may be, times the cosine of 60. And this one would be the force due to gravity times the sine of 60. So before we move on, what is the force due to gravity? It's mg. And I told you all a sneaky way to get around this is that you can just pick a number for the mass because it doesn't matter. But I'm going to just leave it in there and let it get out of the equation when it really divides out. Okay, so there's our components. And actually, I want to draw a new free body diagram. That should be tilted way more than that one. Okay, so remember, this thing is going to accelerate down the hill. And I'm going to draw all the forces on there. So x forces, I'll draw those in red. We have m times gravity, mass times gravity, 9.8, times the sine of 60. And then in the negative direction, we have the force of friction, which is equal to 0.2 times the normal force. Here we still have normal force. And then this direction, we have the force of gravity in the y direction, which is mg cosine of 60. Moving forward. If you look in the y direction, so up and down, you would say the sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. That's Newton's second law. But is this accelerating in the y direction? Is it, lifting off in the y direction? No. So the acceleration is 0, which means the sum of the forces in the y direction, they'll just add up to nothing. And so from that, we conclude that the normal force is the same as the force of gravity in the y direction. It's just in the upward direction instead of downward. It's mg cosine of 60. And yes, I drew all those forces in the same color. Okay. Sum of the forces in the x direction. So that would be this force and this force. Okay. They are equal to mass times acceleration because of Newton's second law. So does it accelerate in the x direction? It sure does. It says it's placed on there. Experience tells us it's going to accelerate down the hill or down the incline. And the problem says to determine the acceleration. So if there's a net force in that direction, it will accelerate in that direction. So we're going to see if there's a net force. All right. In the positive direction, or down the hill, we have mg sine of 60, that one. And then in the negative direction, we have the 0.2 normal force. So mg sine of 60 minus 0.2 times what? Normal force. mg cosine of 60. And here's where things go well for us. Mass is in every single term, so it can divide out. We're left with 9.8, that's what g is. Sine of 60 minus 0.2 times 9.8 cosine of 60 equals the acceleration. So the acceleration of the block bias down the hill is, move this over a little bit, 9.8 sine of 60 minus 0.2 times 9.8 cosine of 60. Make sure your calculator's in degree mode, not radian. Whoops. And we get an acceleration of 7.5 meters per second squared. That's pretty impressive for only being told the angle and the coefficient of friction. That's the acceleration. It's a good problem. It doesn't use mass, but you could if you wanted to, because it doesn't depend on the mass. Well, better yet, everything depends on the mass. And so, because the right side and the left side both depend on mass, if mass increases, it increases everywhere. And so we can divide it out.